Welcome, Professor. Sir.
Good afternoon, Professor Jha. Professor Jha.
Good afternoon, Professor. Professor, sir, good afternoon.
Hello, can you hear me now?
Yes, sir. Now we can hear you.
Okay. Sorry, because I was muted.
Sir, it's okay. Very good afternoon to you.
Yes, madam. Yes, please.
Sir, we will start this program shortly. Just we are waiting to participant to join. We will start it in couple of minutes.
Just open. I will say hi to Professor and Professor, good afternoon, Professor. Professor, am I audible? He knows. Professor, am I audible?
Couldn't hear. Hello, Jaya ma'am.
Yes.
Is he talking because his mic is not showing the audio fluctuations? Professor Prafulla sir, can you hear me? Professor sir. Hello. Professor Prafulla.
Yes.
Yeah. Yes sir. Can you hear me audio?
Yes.
Yes sir. Okay. Welcome, Professor.
Yes. Thank you.
Dr. Jayalakshmi now tried to talk with you, but your mic was couldn't. Now, Dr. Vijay ma'am, Jayalakshmi ma'am.
Shall we start, Beena ma'am?
Just a minute.
Yes, madam. No, isn't Egypt? No, but I'm. Yes, am I? I'm not audible.
Yeah, you are audible.
Sir, you are audible.
Yeah, you are audible. Perfect. No issue.
Okay, okay. Actually, Dr. Jai Lakshmi called me and she said that she cannot hear me. So
No. It was earlier we have identified the problem, but now the problem is resolved, Professor.
okay.
Now it
No,
is
no,
okay.
even I have resolved my problem which I was having with the students in the head's office, right? So now I'm here, so you can start whenever you want.
Yes, sir. We will start in couple of
We will
minutes.
start couple of.
Yeah, not an issue. Please.
Good afternoon to everyone present here. Once again, I welcome you all to Virtual International Conference on Hierarchical Structure Material 2022. For this session, our next speaker is Professor Prafulla Jha. Now I request Dr. Sarvanan, Assistant Professor, Department of Physics, SRMIST, Ramapuram, to introduce our speaker to the audience. Sarvanan, sir?
Yes, ma'am. Yes. Am I audible, right?
Yes, sir. You are audible.
Very good afternoon to all present in this conference. It's my privilege to introduce Professor Prafulla K. Jha to this international conference on hierarchically structured materials 2020.
Hi, Sunil. Oh, correct.
Professor Prafulla K. Jha is presently a professor of condensed matter physics at the Department of Physics, MS University of Baroda, Vadodara, India. He also served as a full professor for about 6 years at MK Bhavnagar University, Bhavnagar. He completed his MSc from University of Pune under the joint Tata Institute of Fundamental Research UGC and Pune University program and PhD from Barkatullah University, Bhopal. He received several recognitions, awards such as postdoctoral fellowship by the Ministry of Education and Culture, Government of Spain. Professor Jha is an Indian National Science Academy Teacher Awardee for the year 2018. He received prestigious tours UNESCO Associateship twice, and he is also a regular associateship of International Center for Theoretical Physics, Italy. He is a fellow of Royal Society of Chemistry, UK also. His research deals with the complex issues and key global challenges using a wide range of disciplines, such as from core metals to environmental hazardous gases for the prosperity of globe. Mainly, his research work focuses from theory to applications in the field of drug designing to cure cancer, bioconjugation for the delivery of neurotransmitters, oxide-supported heterogeneous catalyst for the application in fuel cell semiconductor, nanowires, superconductivity, etc. Professor Jha has published more than 280 research papers in the reputed journals and serving as a member of many editorial boards of several journals. 20 students have been awarded doctoral degree under his guidance, and 8 students are currently working on. He has completed 20 research projects, including 5 international projects from major funding agencies, and his H index is 32 with the citations of about 4,100. So with this small introduction, now I request Professor Prafulla K. Jha to share his findings. Welcome, Professor. Professor, now you can start.
Thank you. Yes.
Now you can share your screen, Professor.
Raj, right, and thank you very much to you all, and for inviting me to this conference and giving me opportunity to speak before you and the audience of this conference on one of my topic, we can say, that is because I work in variety of areas. So in one of topic here I have selected, that is the thermoelectricity. So I will be talking today on this, and let me share the screen first. So is my screen visible?
Yes, Professor, it's visible. Make it full screen. Full screen.
Okay, I have made it right. Okay, fine. So I think it is, my screen is visible, and all, as you all can see, the topic of my today's presentation is, as I said, for the thermoelectricity.
Professor, sorry to interrupt. Your screen is visible, but it is not in the full screen mode. You make it as a full screen mode, Professor.
You reshare it, Professor. You start sharing and then you reshare it.
No, this is in full screen only. I have.
Yeah, it is visible to you as a full screen in mode, but for us, it is in.
It's not in full screen mode.
It is not in full screen. Reshare it. Reshare it. No problem.
Okay.
You quit from the sharing. Again, you reshare it.
Okay. Is it okay now?
No.
No,
Okay.
Professor.
Please put in a presentation mode. Presentation mode.
Okay, let me unshare it, and then I will.
Yeah. First, you open the full PPT, Professor.
Uh,
After sharing, make it as a full screen.
I did that only. Okay. And I have stopped sharing, and now again I will share. Let us see that what happens. Is it okay now? No.
No, Professor. No. Your screen is visible, but not in full screen mode.
No, but it is in mode only. Participant 22 there. I have shared, in fact, that has also gone.
So first to open the PPT.
Yes, I have opened it.
Open it. Now you go to the sharing span. In the sharing pan,
Yes.
you opt that PPT. Yeah. Now you can make it as a full screen. Now you make it as a full screen. Yes. Click it. Yeah. Perfect. Yes, Professor.
Okay.
You can proceed now.
Okay. For me, anyway, but it is same as it was, right? So as you all can see, that the topic of my presentation is drilling deep into the phonon and anisotropic transports of some two-dimensional and phonon glass electron crystal, right? So, as I said, this is basically the thermoelectricity which I will be talking. And the importance of thermoelectricity, as you all can understand from the fact that in the recent years, this net zero terminology is coined, right? And that basically refers the balance of the amount of greenhouse gas emission produced and the amount removed from the atmosphere. And for many companies, many countries, and many states, this has become very important. And in fact, they set this zero target, which is a difficult task. In fact, the United Kingdom was the first country who basically put this target at 100%. But and then later on, Sweden, France, Denmark, New Zealand. Even in the case of Hungary, it is a rule passed from their government. But it is a difficult task to get the net zero terminology, or net zero, that means concept. A lot of progress is being done, but of course it is slow. And it is slow because it is difficult to attain. And this will happen only if we can identify the technologies and can accelerate development and investment in them. That means basically we have to develop the technology. And for this, there are multiple areas, right, where new technology can assist in energy growth and storage, including photovoltaic. You can say that the turbines, hydrogen economy, caloric materials and batteries. And in such class, the another one material is that is the thermoelectric materials. And the thermoelectric energy conversion materials are identified as one of the key area to attain this net zero value in terms of the emission, or maintaining the balance between emission and the use. We know that three materials are basically obtained through the temperature difference, right, which generates the electricity. And in this particular figure, you can see that the difference between hot and the cold region is maintained. In fact, there is a temperature gradient, and that basically leads to the electricity. In these figures A and B, you can see the total energy consumption, how that is increasing. And in the lower part, in the pie graph, you can see that only in the 2015 share of energy, and for the renewable energy, what is the percentage. So these are some aspects which is a known fact, and people are trying to develop the thermoelectric material in that sense. And therefore, in the recent years, this thermoelectricity and the thermoelectric materials have gained the tremendous importance. And that you can see from these two graphs. One, that is thermoelectric papers, that is research papers, till 1988, you can say, till 2021. And you can see that it is increasing rapidly. Apart from that, rate of publication of thermoelectric papers are also increasing. That you can see in the 2021, it was very high. So rate of publication is also increasing tremendously in the field of thermoelectricity method. To get the thermoelectric materials, normally at present, there are three approaches. One is the traditional experiment. Then you have the physics-based computational approaches like density functional theory, which I will be talking. And the third is the machine learning-based data-driven approach, right? And in this regard, some success with limited publication is seen, and the difficulties are basically in that is in the for the traditional experimental approaches are not efficient way of exploring new unknown chemistries, and focus mostly on modifying the known materials by doping or maybe nanostructuring the material to make its thermoelectricity parameters better. Another is the high fidelity physics-based models like Dept, which are computationally prohibitive in many cases, right? And the third one is third one is for machine learning, which basically tells us that it requires a large number of large data, that means multiple data is an expensive process to obtain it. So all these three methods have some sort of limitations, but still people try. And in both cases, whether you go for A or the B, that means for a DFT calculation or the experimental technique, this is the materials are basically modified based on the chemistry and its characteristics in terms of doping or by nanostructuring this. Right. So as far as thermoelectric materials are concerned, the aim is what? That aim is to maximize the figure of merit, which is given by an expression Zt, which is the mean temperature, sigma S square T by K. Upper portion is basically the power factor, and this K is the conductivity. Increase of Seebeck coefficient, that is S, that is as the ratio of voltage generated to the temperature difference. So you can see here that you can increase the jet either by increasing the power factor or lowering the thermal conductivity. So, but they have the relationship which basically interplay between it. That means if you increase by nanostructuring, doping, etc., there is a possibility that the power factor increases, but the conductivity decreases, or vice versa. If both increases, then also there is no effect. So decrease of thermal conductivity is one parameter which is basically thought in recent years to increase the Zt, that is figure of merit for the material. This K contains the electronic contribution and the lattice contribution. But just now, which I mentioned, that if the interplay relation between power factor and the conductivity, that is mainly with the electronic conductivity, right? But other part, which is lattice thermal conductivity, is a parameter which basically we can control or we can modify, or by reducing the lattice thermal conductivity, we can increase the figure of merit Z, right? And that is what is the aim, and that is what is the aim of my presentation. In last few years, you can see that though it started long back, maybe in the 1950, with a very popular material Bi2Te3, right, with Zt having only 0.5, but in this region, that is 1995 to 2015, the most of the materials have been researched, and it is found that the large number of materials have the Zt between 1 to 2. That is, this is what some materials, of course, have the higher value also, but this is what is the value of materials, which value of Zt which is found. See, in the beginning, it was of interest to have the Zt value up to 1, right? But it has been surpassed long, and now people are trying to have the Zt value more than 2, right? And that is what is aim. And you can see that some of the materials here, right, that is basically this one, PBSCTE, you can see that they have the Zt value even more than that. Now, as I said, that there are two aspects, electronic as well as the lattice. So we must see that, of course, I will not go into this part as much detail as in the lattice part, but you can see here that how basically one can tune the electronic properties for thermoelectric material. That means basically what are the best electronic properties for thermoelectric material. If you simplify, you can further simplify that the best electronic structure for thermoelectric material. So of course, I have considered few parameters. You can see here that the power factor for most of the materials basically lies between 0.8 to 2 or something, and the highest value, right, for the power factor is basically for this particular material, right, YBAL3. Similarly, this is for the N type. Similarly, for the P type, you can see that in the range of temperature from 300 to 800 Kelvin, you can see that most of the values are basically below 2 watt per meter Kelvin, right? So this is how the important factor related to the power factor is there. Now here, because I was talking about the electronic structure, so you can see here that is the most importantly that what are the parameters in this particular. Here I am trying to tell you that is what should be the band gap of the material which will be best for best thermoelectric materials, right? In this particular graph, you can see the Seebeck coefficient is a function of only 4 parameters. Those are band gap, position of the chemical potential, energy, that means basically energy exponent, and then the effective relaxation time. Here in this particular graph, if you see, you can see that at 8 kVt, that is when the band gap is around 8 kVt, then it basically converges. But the changes start happening around 4 kVt. So it is found that when the band gap is around 8 kVt, right, then the ZT can be maximum. Of course, these are with some fixed value. Similarly, for the power factor, we can see that for the kVt around 8 to 10, if you have 8 to 10 kVt, then the power factor is maximum. And similarly for the figure of merit. So one can control the figure of merit by controlling the band gap, right, or modifying it. Another parameter basically which affects the thermoelectricity through Seebeck effect is the carrier concentration. And this is another aspect of the band electronic structure, that Bi2Te3 is one of the best material for the highest figure of merit, or in fact you can say the one of the best thermoelectric material. And these are basically the value. So in this case, you can see here, if you count, there are the 6 values in the conduction band, but it is found that if there are 4 to 6 values in the conduction band, those type of materials are good for better thermoelectricity. And just in this side, you can see the gallium arsenide, which has only 1 conduction value, and that is why it is not good. So what should be the strategy, right? So a strategy to enhance Seebeck coefficient, and that can be done by quantum confinement. That means making the materials at lower dimension, or in fact by nanostructuring. A strategy to enhance electrical conductivity can be done by modulation of doping, crystalline alignment, composite engineering. So a strategy to enhance simultaneously the electrical conductivity and Seebeck effect is the carrier pocket engineering and convergence of electronic band, invisible dopants, interfacial effect. So basically the things come finally to the modification of the electronic bands or electronic band structure, which will be affecting or which can be used to give you the best thermoelectric material in terms of the figure of merit. This is something which I have mentioned in the beginning, and now also, that quantum confinement and the structuring of the material is important aspect. And what happens in the case of, you can see here, these are the parameters. It's a physical length scale. And rather, you can say this is something which depends, which is important for the Seebeck coefficient. And this is density of states. And therefore, by modifying the density of states, one can modify the alpha and then finally the figure of merit in terms of the power factor or in terms of the Seebeck effect. So, as I said, that our aim is basically to maximize the figure of merit, and we now focus, right, apart from the factors which affect the electronic part, now we will focus on the lattice part. That means basically we'll be talking about the lattice thermal conductivity, right? So what is basically what are the important factors basic to have the lower lattice thermal conductivity? So first we will see what is the reason for having the higher thermal conductivity. So what happens, due to the mirror symmetry of planar structures, some flexural phonon modes cannot be effectively scattered. So scattering is a parameter that we'll see, and thus have long lifetimes. which lead to uh, which lead to very high thermal conductivity, right? That means if we can control the lifetime or the scattering parameter, then naturally you can control the lattice thermal conductivity, right? And therefore, by the Strack's theory, that reveals four factors which lead to low KL: complex crystal structure, high average atomic mass, weak interatomic bonding, and a strong enharmonicity. So enharmonicity is an important parameter that basically is responsible for enhancing the quality, or other you can say lowering the KL and enhancing the figure of merit. You can do with the defect, and therefore in recent time the two-dimensional transition metal dichalcogenides have been found with very lower thermal conductivity values compared to that of graphene, and reason for that is basically the buckling. As I have mentioned here, the planar structure has the drawback to give you the high thermal conductivity. Then it is the quantum confinement, right? And then the combination of different bonding types leads to complex crystal structure with the possibility of multiple structure units in the same structure, right? So these are some parameters which basically leads to lower thermal conductivity, lower lattice thermal conductivity, and that will be useful for having the higher ZT or the figure of phonons. Anyway, we all know that is a quantum of lattice. So what is that? So if we want to control, tune, modulate the lattice thermal conductivity, we have to tune, modulate, and modify the phonon dispersion curve of the material, right? And that will have several parameters, such as I mentioned, the scattering rate, then the lifetime, then it will have the several enharmonicity, other parameters, those parameters. So phonons are basically the quantum of lattice vibrations, and they are useful in several things. Those who are from the solid state physics can recognize, understand the lattice dynamics, the stability of a structure in particular phase. You can understand phase transition. You can understand vibrational spectroscopy, electron phonon interaction in superconductivity, or of course this electron phonon interaction is important nowadays even in explaining the thermal conductivity, right? So that is there. So you have for usual materials, bulk materials, or maybe the simple material, you can say that you have the acoustic phonons and the optical phonons. And when you have two-dimensional material, in that case you will be having, apart from this transverse acoustic, transverse optical, longitudinal acoustic, longitudinal optical, you will have additional branch of phonon. That means the out of plane acoustic mode and out of plane optical mode. This is a characteristic feature of the two-dimensional materials, right? So this is how the phonon dispersion can be determined through theory and through experiment. So I will not go to this, just these are the methods. Normally the thermal conductivity is calculated using the Boltzmann transport equation, right? Boltzmann transport theory, and this is what is the expression for KL, and you can see this omega L is nothing but is the group. This VL is V lambda is group velocity, tau lambda is the relaxation time, and the omega L is the angular frequency. So you can see here that these quantities can be tuned by the phonon dispersion curve. Another parameter is basically that is the Gaussian parameter, which is a descriptor for estimating the thermal conductivity. So these are the parameters which basically reflects that how thermal conductivity can be controlled or modified and what will happen. So the whole our methodology based on the first principle density functional theory, and I'm sure you all must be knowing it. This calculation basically gives you a structural, electronic, and vibrational property. And for other purposes, we use the Vanier tools. Codes have been used, VAST and the quantum espresso. Then we run the SENG-BT code for calculating the thermoelectric parameters. So these are how the basically the matrix. Because we are talking about the two-dimensional material, therefore we can not leave the graphene. And the graphene, as we know, it is a single atom thick sheet of carbon atoms that is arrayed in honeycomb pattern, and is the world's thinnest, strongest, and stiffest material. And of course, it has wonderful properties, and that is why it is also called as the wonderful material. This is the phonon dispersion curve for the graphene. This is the Raman spectra. So without going into the details, just I will tell you that several information about the material can be obtained from the phonon dispersion curve, such as you can know the electron phonon interaction, right? If you know the slope around gamma point and the K point, K is the Dirac point of this, right? You can know the number of layers to this. You can find out the chemical doping and several aspects. This is just a calculation. You can see from here, that is how the phonon dispersion curve looks like. You can see here, this is what the ZO and this is ZA, which is the out of plane acoustic mode and out of plane optical mode, right? And this is for the single layer, this is for the 4 layer, and you can see here that for the ZA, you have the 4 different branching in the book beginning. Just you can tune the phonon dispersion curve for the graphene by oxidizing it, right? And these are all the graphene oxide, and you can see there are different models for the graphene oxide, and by having the ratio between carbon to oxygen, one can vary the band gap from 0.8 to 4 electron volt. So basically what that you can tune the phonon dispersion curve, right, to get the phonon related properties of the material, right? Now, since we are trying to see that how they affect, therefore I have selected the allotropes of boron nitride, right? And in that I will be considering cubic boron nitride, bulk hexagonal boron nitride sheet, boron nitride nanotube, and the boron nitride halide. Just for reference, of course, these will be seen later also, but you can see that for all 5, the phonon dispersion curves are different, right? With, of course, there will be some similarity at some point, but in general, if you see, there is a lot of difference, right? For example, it is cubic boron nitride, and you can see in that no out of plane acoustic and optical mode. When it goes to bulk hexagonal boron nitride, because that is a layered structure, as you can see from here, you have the out of plane acoustic mode and out of plane acoustic mode. Then it is the 2-dimensional boron nitride sheet, and you can see here that the phonon dispersion curve has the nature, of course, similar to the bulk hexagonal boron nitride sheet, but with a different nature. This is for the boron nitride nanotube. You can see the dispersion relation. This is for the boron nitride halide, a different structure. And you can see here, because the unit cell contains more number of boron and nitride, therefore it has large number of phonon modes, right? So you can differentiate, you can see the different phonon dispersion curves for different boron nitrides in different cases. The phonon dispersion curve also can be tuned by applying the strain, and that you can see, and that basically the strain is useful in tuning the band gap, right? Our study is theoretical study, but in the experimental you can see there that by having the strain, of course there is change in the lattice parameter. This is the strain percentage, because this is an experimental study, and you can see that the band gap varies. And that is what we also found in our studies, that is strain for different percentage of strain, you have the different band gap. So band gap can be tuned with by applying the strain. And so is the phonon dispersion curve, right? So for the different strain percentage, you can see that is for the 2 to 18% strain. You can see that the phonon dispersion curve, nature of phonon dispersion curve is changing. Particularly, one thing you can focus, that this is what is the out of plane acoustic mode. And finally, you can see as you go on increasing the strength, this particular line, that is out of plane acoustic modes, become linear, right? And this also gives some indication about the rippling in the graphenes, right? Now, for different systems of boron nitride, you have different energy gap, right? They are structural parameters, so we leave it. Now here you come phonon dispersion curve for the bulk DN. This is the two structure for the hexagonal and the cubic boron. So you can see here in the bulk hexagonal nitride is a layered structure, as I have shown you, with 4 atoms per unit cell. While cubic boron is the face-centered cubic structure with only 2 atoms per unit cell, and that is why phonon dispersion curves are different. Due to a stacking of layers in bulk hexagonal out of plane ZA mode is obtained. In the case of cubic boron nitride with face-centered cubic structure, only 2 TA transverse acoustic and 1 LA mode is observed. So this is what is the difference, right? Now we come to the bulk 2 layer, that is mono layer or 2-dimensional, right? So you can see here, this is basically the eigenvalue pattern, eigenvector pattern. But here you can see in the dispersion curve that this is for the bulk and this is for the 2-dimensional cases, right? So you can see that not only the value changes, right, but the nature of the phonon dispersion curves also change, and hence they will have impact on the phonon related properties, particularly in our case for the lattice thermal conductivity. Halide is another material made up of boron, right? With it is basically after applying the strain, you can say that this is a square octangle pair in hexagonal boron was predicted long back, and of course that was also observed in the gallium nitride, and this is what is the dispersion curve, right? And as I have already mentioned, but we observed that a strong coupling between acoustic and optical phonon modes leads to low lattice thermal conductivity. And if you remember, I said while discussing the quest for the lower thermal conductivity that if there is a coupling between the acoustic and the optical phonon, that is good for low lattice thermal conductivity. Then Grunjan parameter for halide and the 2D HBN, then it is the anharmonicity. You can see here, right? So the anharmonicity is lower in the case of 2-dimensional hexagonal boron nitride in comparison to the halide boron nitride, right? Here it is in the up to 200, you can say. So that means the anharmonicity increases. Therefore, it is expected that the halide boron nitride will have the lower lattice thermal conductivity. When it comes to the Grunjan parameter, you can see that the contribution from ZA, contribution from TA, LA, and optical modes. And here you can see again in the halide boron nitride, the Grunjan parameter is much higher in comparison to the Grunjan parameter in the case of 2D. That means one can tune the phonon dispersion curve in such a way so that the Grunjan parameter, anharmonicity, and etc. is increasing, and finally it lowers the lattice thermal conductivity. Now here you see for the 2D hexagonal boron nitride and halide boron nitride, the lattice thermal conductivity is high at room temperature. It is around 600 watt per meter Kelvin, while in the case of halide boron nitride, you have only up to 60. So what is the reason for that? So acoustic modes contributing mainly to the lattice thermal conductivity, right? That we have seen from here. That is the major contribution is from the lattice, from the acoustic phonon modes, right? So higher value of Grunjan parameter and larger anharmonic scattering, which we have seen in halide boron nitride, is responsible for lowering the lattice thermal conductivity. From the phonon dispersion curve of hexagonal boron nitride and halide boron nitride, we can see the slope of acoustic phonon modes are lower for halide boron nitride, which makes reduction in the group velocity in halide. That means what? that the group velocity should be lower, right? That means if the slope is lower of the phonon dispersion curve, that will lead to the reduction in the group velocity, and if it reduces the group velocity, naturally you will have the lower thermal conductivity. So the point you can basically see, right? I will, right? So this is now another boron nitride thing, that is like the graphene oxide, hexagonal boron nitride oxide, and you can see the phonon dispersion curve in comparison to the hexagonal boron nitride, Heckelite boron nitride, and how the dispersion. So there is a lot of overlap, or basically a strong coupling between the optical and the acoustical mode, right? And this is what we have just discussed. This is for the band structure. You can see the hexagonal boron nitride, you have the band gap of 4.63 electron volt, while in the hexagonal boron nitride oxide, you have the band gap of 0.7 electron volt. And of course, then chemical potential, then the relaxation time, and other parameters are also important, which you can see that can be tuned through the band structure. And here, that is basically the band structure is being tuned. Another aspect for the BNO is what? That is highly anisotropic, right? And anisotropicity is basically found to increase the lattice thermal conductivity, right? So you can see for the hexagonal boronite, there is no imaginary phonons, additional 4 branches for consisting 2 bending and 2 stretching at higher frequency region, reduction in frequency of acoustic mode. You can see that acoustic mode in this hexagonal boron nitride is high. Highest frequency of boron or nitrogen in hexagonal boron nitride oxide is less than that in hexagonal boron nitride due to oxygen atom along z direction. So that is where the anisotropy basically comes. Oxygen atom diminish harmonic force constant and increase mass density in BNO as compared to hexagonal boronite, which reduces the acoustic mode frequency. That is also good for lower lattice thermal conductivity. So you can see that these are the parameters which basically leads to the reduction in the lattice thermal conductivity. These are all parameters anyway we have explained. Just you see here hexagonal boron nitride and boron nitride oxide, that K lattice for the boron nitride, right, is much lower, right? That means at room temperature it is 100, while for the hexagonal boron nitride it is around 300, right? So high value of Grindel parameter is responsible for reduction in lattice thermal conductivity in hexagonal boron nitride oxide. Acoustic phonon modes contribute mainly to the lattice thermal conductivity. Lower slope of acoustic phonon mode for hexagonal boron nitride oxide is responsible for reduction in group velocity. That will lead to the lower lattice thermal conductivity and finally. Right. This is the benchmark materials for the thermoelectricity. So here just I will show you that is how a structure matters, right? So GET is an interesting material which is in ground state. It is a rhombohedral structure, and then the excited that means for that high pressure it is in the CSCL structure. To go from rhombohedral to a CSCL structure, there are 4 parts, and this is the simplest part. So let us talk about this, right? So you have rhombohedral R3M, you have NaCl FM3M, and you have the CSCL structure PM3M, right? That is basically the this structure. And therefore you can see that rhombohedral to NaCl it goes at 3.5, and from NaCl to PM3M, in fact, this is some mistake. So it is 34.5 dPa, right? So there is a phase transition in of the GET. So you can see the from phonon dispersion curve, rhombohedral is stable at ground state, or the cubic is not, or similarly the orthorhombic is not stable, right? Because of the imaginary phonons in these 2 cases. Of course, these 2 can be made, right, stable by applying the pressure, and you can see that FM3M, right, that the cubic, which was unstable at 0, becomes stable at 3.1 GPa, right? So, and that is what is the phase transition pressure for FM3M also. That is from rhombohedral to Q. Similarly, for the PM3M, you have from 0, you have full imaginary phonon, but at 33 GPa, which is basically experimentally 34.5 GPa, is this, right? So, cubic at 3.1 has real phonon modes, a stable structure. Similarly, for PM3M at 33 GPa, it is stable. So here you can see the lattice thermal conductivity for all three structures, and you can see here that is the minimum value for the lattice thermal conductivity is, of course, that is for the FM3M. But at normal condition, it is not stable. Therefore, we can say that even for the R3M, the lattice thermal conductivity is much lower. Right now, we can make the structural. One can make the germanium telluride and germanium selenide monolayers, and by the exfoliation process of GET, we can. This is the cleavage energy, so we can have the single layer of that with this much separation. And you can see here the phonon dispersion curve for both GET and the GEC with a very minor imaginary phonon modes, right? So this is, you can see that nature of the phonon dispersion curve is more or less same, except the values of frequencies. In the lower part, we show that is the eigenvector, right? Now here you come. So here you have the group velocity, you can see for the bulk GET, right? You can see that for the bulk GET, the group velocity is very large, right, up to 8. But for the two-dimensional GET, the group velocity is lower. And as we have discussed, that if the group velocity is lower, the lattice thermal conductivity will be lower, right? Similarly, for the Green parameter, you can see, but this is interesting to see and observe, right? And therefore, in the K lattice, right, that is lattice thermal conductivity for two-dimensional GET is maximum at 0.5 at 300 Kelvin, while in the bulk GET, you can see it is around 3 at room temperature. So the point is that for the monolayer, you can have the lower lattice thermal conductivity. That means it is nothing but it is nanostructuring the material, right? And this is again all other group velocity, and the specific parameters for the GET and the GESC. I will not go into the detail, but what I wanted to convey that had been conveyed. And here you can see for the GET monolayer and the GESC monolayer, you can see for the GET, the lattice thermal conductivity is lower. Therefore, GET is better thermoelectric material than this, right? Higher values of Green parameter, as we know, leads to the strong inharmonicity, and that will lead to the lower lattice thermal conductivity, right? So that is what it is. The another class of material is the topological insulator, and I will not go into the topological part, but only I will tell you that this is for a half Heschler compound. We have calculated the lattice thermal conductivity, and this is all related to the topology, so I leave it. But you can see here that thermoelectricity is obtained a remarkable thermoelectric property, that is ZT value is obtained 0.55. That is only the electronic part, that is not the lattice thermal conductivity is basically added, right? So here you can see the ZT with temperature for different carrier concentration and right? In the recent time, right, what happened in the recent time, the people have started applying the concept of electron phonon coupling to predict the correct thermoelectric parameters, right? And it is found that the lattice thermal it is found that the electron phonon coupling, right, basically reduces the lattice thermal conductivity. So without going into detail, also just point in that one can reduce the lattice thermal conductivity if one properly takes care of the this takes care of the electron phonon coupling in this. Here you can just see in view this particular diagram, right? This is for a different compound. So here just I will show you in this, right? This is for simple pseudopotential. This is for pseudopotential including the electron phonon interaction, and you can see that lattice thermal conductivity decreases, right? Even in the case of ZNC. So the point is what? The lattice thermal conductivity can be reduced by the electron phonon scattering greatly at higher concentration, right? The strong polar LO phonon scattering is mainly due to its large EPC strength. The results suggest EPC plays an important role on the thermoelectric properties, and the full evaluation of EPC is necessary, especially for polar matter. So one has to consider the electron phonon interaction, right? And in the recent past, right, in the recent years, in fact, you can say very this electron phonon interaction has gained the importance to be included in the transport properties of the material, right? This is a material that is calcium antimonite, and this is basically a class of material phonon electron gas crystal, which is you can say the electron crystal like electronic conduction and glass like low thermal conductivity. So basically phonon electron gas crystals are where that is this, they are combination of metallic character as well as the glass character, and its properties are what? That generally form layered structures sandwiched between the cation layers, and due to such atomic configuration and trigonal symmetry, the enharmonicity is present, right? That means the in plane and out of plane ratio of electronic and thermal property evidently changes. That means basically the enharmonicity is increases, and therefore it has the remarkable enhancement in thermoelectric power factor on introducing the chemical doping and the low band. Right, this is what is the band gap. You can see with the spin orbit coupling or without spin orbit coupling, right? This is the phase space, but point here is that you can see the group velocity. So group velocity is lower, right? It is maximum, that is around 2.5 kilometer per second. This is phonon dispersion curve, density of a state. So high 3 phonon phase space for acoustic modes that indicate that high acoustic phonon scattering rate, right? And you remember that scattering rate basically is responsible for giving. So these are the parameters we have calculated by considering the spin orbit coupling as well as the enharmonicity. Enharmonicity is an important parameter that is basically obtained. That is, you can say the third order interatomic force constant is obtained from the second order force constant, which is obtained from the at the time of phonon dispersion curve. Then a big supercell is prepared. Then the big supercell is optimized, and so it is a costly computation anyway. But it is important to be included to have the correct value. So high power factor, low lattice, and electronic conductivity, that basically leads to the phonon gas electron crystal strategy, right? And at room temperature, the ZT value is obtained at 0.7, right? This is for the gallium nitrides, which just I have shown you in the introduction, where only one single value is there, and that is why you can see here that the thermal conductivity is very high, right? For these compounds, right? So I will another important aspect is related to the imaginary phonon in 2D materials, right? As you can see for the GET, the phonon mode, that is for the out of plane acoustic mode, you can see there is a imaginary phonon at zone center. But when we calculated, of course, with the higher parameters, right? That means for the energy cutoff, mass, that those things were taken higher value, then of course we could get it. So point is what? That if you want to have the correct value, you have to go for the computationally costlier calculation, right? Because sometimes what happens that you calculate and you obtain the imaginary phonon, let us consider. And if you perform the same calculation with the higher level parameters, you will get the better values, or I mean the correct value. So that one should see that whether it is a computational limited error, or it is basically the characteristics of material. Because then we checked in another material, that is SiG monolayer with buccal, and as we increase the cutoff, you can see that imaginary phonon modes turn to the real phonon modes. That means it is important to check the phonon dispersion with higher value of Q mains, E cuts, size of supercell, etc. That important, right? So for this example, just it was just for interest. So for 200 readword E cut SIG and 110 readword, so you can see, of course, the lattice thermal conductivity is lower, but the structure is not stable here, right? Similarly for the Gaussian parameter. So thank you very much, right? And these are the funding agencies which basically where their funds are basically used for these calculations. And thank you very much. Take care, right? So I stop here. I end my presentation. If and I think I'm exactly in time.
Yes, Professor. You are exact of time. Professor, can you able to hear me?
Yes, I am hearing, madam. I am hearing.
And this is the session for the participants. Participants, if you have doubt, you can interact with Professor. Dear participants, so participants, yes, Professor sir, one question in the chat box. Could you please explain about energy fitting?
Filtering, right? If the candidate can explain me what does mean by what you see or he wants to put from the energy filtering, what context?
Celestina?
Yes,
Celestina?
ma'am. Yes, ma'am.
Just ask your doubt, ma'am.
Yes, sir. Hello, sir. Could you please explain about the energy filtering, the basics, the thing?
No, in what context?
And actually, I don't have any clue about what is energy filtering. So, could you please explain that?
I don't know how this is connected with it exactly. Let me try. Energy filtering means you mean basically how the energy can be filtered with the help of material.
Okay, sir.
Right. Anyway, I will also try to find it out, and then I will tell you, because but the question is not clear to me.
Okay, sir. Okay, sir.
Professor, I have a question, Professor.
Yes, please.
Yeah, Professor, okay, for bismuth selenium, people are going crystal and study the thermoelectric property, and mostly people are using solid state reaction. Okay, which one is the good efficiency, Professor?
Again, repeat it, because last sentence I could not hear.
Yeah, Professor, we are growing crystals for thermoelectric application, and also people are using solid state reaction method. So which one is a high efficiency for thermoelectric application?
Which will give you the higher efficiency?
Yes, Professor.
Oh, sorry, sir, because if you remember, I have done all theoretical calculation based on the computational methods, right? So I will not be able to tell you that that experimental part, that which method is good for synthesizing the material.
Okay, Professor, I have one more, Professor. Okay, can you tell me which one is the highest figure of material?
Which is the highest?
Figure of merit material.
Figure of merit. See, basically the most popular material as far as the thermoelectricity figure of merit is concerned, it is Bi2Te3, right? And apart from that, that is another material, PBT, PBSC, their composites are also found to be with the very high value of thermoelectricity. And if you remember, I have shown in the beginning one particular graph, that is YbAl3 has been found with a maximum value of power factor, right? But what is the lattice thermal, I mean, the lattice thermal conductivity part, that is missing, but power factor is best for YbAl3. But the most popular materials for this good of merit is basically that is Bi2E3, their composites, PBT, PBA, all chalcogen, etc.
So thank you, Professor.
Participants, if you are having more questions, please interact with our speaker. You can post your question in the chat box, or you can unmute yourself and ask.
If you can post, or if you still have problem, you can write me on my email, right? I will certainly answer. Seems no question, madam. So you can.
Yes.
Thank you, Professor.
Thank you, Professor Prafulla, sir. I'm Sudha.
Thank you very much,
Thank you
madam,
so
for
much. Thank you so much. Thank you so much
inviting me to give
for
the.
sparing your valuable time with this.
Thank you, madam. Thank you very much.
Thank you, sir.
Thank you,
Thank you, sir.
Professor Jha.
Thank you, madam. Thank you very much, right, for inviting me. And then, of course, it was. So can I close now?
Yes, sir.
Yes, Professor. Yes, Professor. You can close. Thank you so much.
Dear participants, now we are at the end of our conference, and we will start our valedictory function soon. Please be with us. Dear participants, please be with us. We will start validatory function soon. Feedback link will share after that.
சார் நான் உங்களுக்கு மெயில் பண்ணிட்டேன் சார் லிங்க். அதுலயே ரைட் அப்பும் இருக்கு. அதை தவிர பிரிண்ட் அவுட் Veena ma'am.
Yes, ma'am. Sir, join me.
Joined.
Shall we start, ma'am? Just a minute, ma'am. Subramaniam, sir. Sir is not joined.
Veena ma'am.
Yes, ma'am.
Madam.
Yes, ma'am. We have to give
Have
progress.
to give him flowers. Good afternoon, sir.
Madam, good afternoon.
Good afternoon, sir.
Good afternoon, madam.
Ma'am, you can start.
Yes.
Good afternoon, one and all present here. I welcome you all for the valedictory function of second virtual international conference on hereditary structured material 2022. Now I invite Professor L. Sudha, Professor and Head of the Department of Physics, to deliver welcome address. Ma'am.
Thank you, ma'am. Good afternoon, one and all who have joined this valedictory function of second virtual international conference on hierarchically structured materials organized by Department of Physics for the 2 days, and today we are going to have the valedictory function. I take privilege in welcoming VP Admin Sir of SRMIST of Science and Technology, Ramapuram campus. Welcome, sir. And I also welcome other participants from other institutes, colleges from all over India. And I take my wholehearted thanks to all the resource persons for the past 2 days. I welcome you all. Thank you.
Thank you, ma'am. Now I welcome Vice Principal Admin, SRMIST Ramapuram campus to give valedictory address. Sir.
Thank you, madam. Good evening to all. I feel happy to join the valedictory function of second virtual international conference on hierarchically structured materials organized by the Department of Physics on 25th March 2022 through Zoom platform. The Department of Physics organizes conferences, seminars, FDPs, workshops, competitions every year. In this conference, the resource persons are from reputed universities like University Paris, France, University Cloud, France, University of Cambridge, United Kingdom, University of Greensboro, USA, IIT Hyderabad, and various reputed universities. This conference is conducted for the benefit of faculty members, research scholars, and UG students. The Department of Physics is conducting the conference in series for the past 10 years with the same title, which focuses on materials for various applications. I appreciate the department faculty members for organizing this conference, and I wish them success in all the years ahead. Thank you.
Thank you very much, sir. Now I request Dr. T. Beena, Assistant Professor, Department of Physics, to present conference report.
Good evening to all. I take immense pleasure to share the report of our second virtual international conference on hierarchically structured materials, ICHSM-2022. We have started the first day of ICHSM-2022 with the inaugural function with the chief guest, Dr. V. Kanchana, Dean Faculty, IIT Hyderabad, Telangana. Dr. L. Sudha, Professor and Head, and also the convener of the conference, has given the welcome address, and our Dean, ENT, has given the felicitation address. Our chief guest, Dr. V. Kanchana ma'am, has given the keynote address. Our conference e-proceedings were released by our chief guest, chief director, and was received by our director, Dean ENT, and the convener of the conference. Next, the plenary talk was given by Dr. Jiban Powder from the Department of Chemical and Biological Engineering, Canada, and Dr. Mohammed Juni, Professor and Head, he has given the plenary talk on the title, Covalently Linked Dihole Transporting Material Improving Charge Transfer in Solid State Dye-Sensitive Solar Cell. Dr. Shrikutan from Scientist, CSIR Secretary, Chennai, he has given a talk on non-precious oxygen reduction reaction electrocatalysis for polymer electrolyte membrane fuel cell. Dr. Sujit Datta, Research Associate from France, he has given a talk on the influence of nano-confinement on the structural, dynamic, and kinetic properties of liquids. Dr. A. Subaya, Principal Scientist, CSIR Secretary, Karaikudi, he has given a talk on carbon-based materials for biosensing applications. And Dr. Kumar Raju, Resource Associate from University of Cambridge, UK. He has given a talk on challenges and opportunities of Mn-rich Li-ion battery cathode materials. Dr. Shanti Iyer, Professor, Nano Engineering, Joint School of Nanoscience and Nano Engineering, North Carolina, A&T State University. She has given a talk on MBE grown GAS SB nanowires for near infrared photodetectors. And in the second day, the session was started with Dr. Supreme Das, Assistant Professor, Department of Industrial and Manufacturing Systems, USA. The plenary talk by Dr. Rabindra Pandey, Professor in Charge, Department of Physics from USA, Houston. And Dr. Rohit Medwal from Resource Associate, Natural Science and Science Education, National Institute of Education, Nanyang Technology, Singapore. He has given an invited talk. And Dr. Shivakumar Manikam, Professor, Chemical and Nano Pharmaceutical Process Engineering, Brunei. He has given a plenary talk. And Professor Prafulla Jha, Department of Physics from Maharajasarya University, Baroda, has given a plenary talk. In almost all the sessions, more than 200 participants in Zoom and YouTube have actively participated. We have received more than 250 abstracts from all over India and 10 abstracts from the foreign universities. And contributory sessions were conducted as a parallel session for oral and poster presentation. There were 95 oral presentations and 41 poster presentations, and participants actively interacted with the resource person, and we have received a very good feedback, positive feedback from all the participants. Thank you.
Thank you, Dr. Beena. Now I would like to invite Dr. Jayalakshmi, Assistant Professor, Department of Physics, to present conference poster and oral presentation video.
Thank you, ma'am. I'm very happy to announce